There aren't that many places that can claim to be as cool as Google, but it does happen. So maybe few of you have heard of Sandia National Laboratories. They have lots of cool hardware in there. They have the biggest laser in the world, and it is a monster. And we have a speaker from there, Brett Bader, but he's not going to talk about the laser. He's going to talk about something that's much closer to us. For me, surprisingly close. I would never imagine that they will work on something like that. Algebraic techniques for multilingual document clustering. So multilingual document clustering is very interesting for us, and we'll hear what Brett has to tell about that. Actually, I met Brett through a colleague of his, Philip Kegelmeyer, sitting there, in case you are wondering. And he has already gave several talks at Google, and I was really impressed by his work. So here he brings us another good thing.
Well, thanks, Moshe. So my name is Brett Bader, and so I've been at Sandia for about a little over 7 years, and I've done a number of different projects. But this work that I'll be talking to you about today is actually a project that started about 4 or 5 years ago under a PI, principal investigator named Peter Chu. He's since left Sandia, but he was the one who kind of kickstarted this work in multilingual document clustering. And I started working with him 4 years ago, kind of bringing some computational expertise, looking at different algorithms and how to apply different algebraic techniques to the problem. So Peter was involved principally with, he's a computational linguistic, he has a computational linguistics background and also worked with a lot of the data. Ron Oldfield is another key person for the work in this talk, and he dealt a lot with high performance computing and the architecture aspects of the work here. And then Philip Kegelmeyer, who also, so Moshe introduced him, he did a lot with the machine learning. So those are the three principal people involved as collaborators, but there are a lot of other folks that were involved with contributing ideas or helping with some of the data analysis, high performance computing aspects, and so forth. So those names are listed there as well. So Sandia has developed some techniques for analyzing documents in a number of different languages, and we're interested in kind of translating these documents into a concept space that's language independent. So we can then apply different techniques like doing document clustering, maybe using some of those features to do cross-language text analysis or classification. And so what I'll be talking about primarily is the document clustering. I guess a sub part of that could be doing translation triage, where if you have some clusters of documents, you could look at those clusters and see what English documents are the languages that you know. And if you're interested in something in that particular cluster, you can then go ahead and spend resources to translate those other documents. I'll talk just a little bit at the very end about two topics in text classification. So one is ideological classification, and another is multilingual sentiment analysis. And so I'll go ahead and talk about those at the end. So I'm sure all of you are aware of this, but just to kind of frame the rest of the talk, I just want to give an introductory slide on the bag of words and vector space model. So if we have a number of documents, we can pull out terms of interest to us. We then have a lexicon of those terms. We can create a bipartite graph consisting of terms and documents, and then take that graph and then take the adjacency matrix of that graph to so we have the number of rows correspond to the terms, and the documents would correspond to the columns. And so this, the vector space model is basically saying that each document can be represented as a vector, a column vector in this sense. And so another aspect here is if we have stop words, we may ignore some of the words like the word the and so forth, the ones that don't really carry much meaning, so we can ignore those, and that'll come up a little bit later. Also stemming, so the word bake and baking are in this list here, but we don't include those as separate terms. We stem, or stemming is a common technique, and you'll see later that we try to avoid that. And let's see, the last thing here is that while this example here shows zeros and ones, we actually may be interested in including the actual term count in our documents, and then do some sort of information scaling. And so this will come up just briefly a little bit later. So our design goals for the work here is to allow as many languages as possible, and we don't want to be constricted or restricted by language expertise. So we don't have to hire some language expert who knows some obscure language. We want to go ahead and just try to do some statistical analysis of corpora and rely on that knowledge. So we don't want to do any stemming because constructing a stemmer would require some language or knowledge of the language. And we also don't want to construct a stop list. So we'll just go ahead and include all the terms that we come across. And so those are the design goals that we've set out in the very beginning, and that's what we've done. So as you might expect, what we do for dealing with multiple languages is we can construct a term by document matrix for each language and then stack those on top of each other. This has been done before with pairs of languages. So Landauer and Littman in 1990 and Young in 1994 dealt with pairs of languages where one of them was English. We've also, so I think some of the new thing here is maybe applying or stacking many more languages on top of each other so we have a much larger matrix and try to look at the co-occurrences across many languages. And so this is one of our contributions that we had early on.
One question.
Yes,
maybe you
question.
said that already, but you know exactly the language of the document, or is that also
I'm sorry, what's the
language of the document?
Oh, so yes, we assume that the language is known, or we know what it is, so that way we can classify it and put it in here. And so we're starting from, I'll say here, so we're using the Bible as our Rosetta Stone. So the Bible has been carefully and widely translated into a lot of different languages, so we actually know which translation we're dealing with, and so we simplify the problem that way.
So you can also assume that each document is only in one language.
Yes, but it's easy, or at least I think we can go ahead and use some techniques. If the document does have multiple languages in it, we can either look at the individual words, and those would fall into some piece of that term vector, and so that wouldn't be too difficult. But the case may be we have some words that transliterations or whatever that may fall in different languages, and so we don't know which one of those, and so we can use maybe a naive Bayes classifier or something to help with that. But we haven't explored that. All right, so the Bible is one of the corpora that we used, and so it's nice. There are a lot of different translations of it. It's also verse-aligned, so each verse is roughly a sentence or two in length. Our particular database has 54 languages. They're all listed here and roughly color-coded by language family. However, I'm not one to, I've not worked with all of these languages. We typically just deal with a few of these for doing our training and testing.
So how does the vocabulary of the Bible overlap with the vocabulary of some
Yeah. Excellent question. So, so the question is, how does the vocabulary overlap with the crawl of the web? And it doesn't necessarily, but we have it does have a lot of terms, and so this table here shows the unique terms for English. So there's 12,000 just in the English translation, the King James version of the Bible, and so we get a good overlap with some of the relatively common words, but we're missing things like technology and politics and some of these more modern ideas. So we can go ahead and extend that with other corpora. We haven't done that to a very large extent so far, but we have worked with Europarl, so the European Parliament proceedings, and so that was something that we've looked at. But our main focus has been looking at threats that are kind of more religious-based, and so that's why we started with the Bible.
Why are there so many more distinct terms in other languages? Is that your stemming is different?
It's because, so the question is, why are there more terms down here in Arabic, for instance, or Russian as compared to English? And the answer is because languages convey different amount of information in their words. And so linguists have kind of classified languages on a spectrum between an isolating language and a synthetic language. And I'll get into that a little bit more. It deals with language morphology. And so that will come up a little bit later.
So just, I'm completely ignorant about this. Is the Quran translated in other languages?
It is, and we actually use that here as well. So we use the Bible and the Quran as our training and test set. All right, so I don't know. Here's just one example of this is just the first verse of the Bible, and you can see the word count, difference as you would expect. Really, this kind of sets the stage for it's an example of what we're doing. All right, so so the approach now that we have is we take this term by verse matrix. We're dealing with 5 languages, so English, Spanish, Russian, Arabic, and French are the languages that we've been using for training and testing purposes, and that's what we published on. And so multilingual sentiment analysis means taking that matrix and doing some sort of a dimensionality reduction using the singular value decomposition, or SVD, and we truncate that singular value decomposition to retain the large, I guess the largest rank matrix that kind of represents this original term by document matrix. We actually keep 300 columns of this matrix here, which consists of the left singular vectors, and so that matrix has 300 concepts, and we've looked at going a little bit less than that, but 300 is the number that we stuck with. Let's see. So we have this matrix here that's an orthogonal matrix. It relates the terms to these different latent concepts that are in the Bible. The V matrix here is an orthogonal matrix that relates the documents back to these latent concepts, and then the sigma here is the a diagonal matrix of singular values.
Sorry, one little question. I probably missed something. So, how do you segment the Bible into documents? How big are the documents? Chapters, lines? What?
So verses. So it's a verse aligned, and so it's about a sentence or two in length. And
Okay.
there's 31,000 verses. So we have 31,000 columns. That verses are what we're considering as our document. That's how it's chunked.
So just to clarify, this is your training step in that you're trying to learn a transition model effectively, right? Because you already
Not a transition model, but just
transition model.
we're just trying to learn latent concepts, and so latent semantic analysis is trying to extract a lower dimensional representation of the original matrix, but it's not looking actually at transitions, a word-to-word type transition, if that's what you're thinking.
Sure, but at this point, your data is that the individual documents are translations of each other, and so you're trying to learn a model.
I'm sorry.
Yeah.
Yes. So we know that, for instance, the verse 1, and so maybe I can go back to this. So we know that verse 1 in English is this. We look at the vector space model of that, and we know that the vector space model of the same thing in Arabic. We can look at the statistical co-occurrences of terms, and so we can see that God created and Crio Dios. Those things always co-occur, and so those we can make that relationship explicit in this matrix, this U matrix, and so we have large values for a particular column. For those particular terms, we could see large values there across languages. That's clear.
Is this slide still monolingual? Like this is just for one language, the SVD?
This is multilingual, so we have all languages, or these 5 languages here. And so in the corresponding U matrix, we'd have English, all the terms for English up here, the terms for Spanish here, the terms for Russian, and so on.
Does that block structure carry over into the projection space?
It should. You should expect to see certain terms, like, so the word God appears a lot in the Bible. So you'd see God, somewhere here is the row for God, and so you'd see large values in that row. And then for Spanish, Dios is the corresponding word for God, and so you'd see large values there as well. And so it's that's where you get the relationship, the explicit relationship between words. Make sense?
I was more interested, if you look at U as you draw it there. No, sorry.
All right. So this first part, what I just described, was a training step. So we have a reduced representation of the latent concepts in our corpus. If we have new documents, we can go ahead and project. We can represent those new documents in the vector space model and project those documents into the space spanned by the columns of U, and so we get then a small dimensional representation of this document here. And I've got here just 20 of them, but as I mentioned before, we actually have 300 columns of U. But just for the sake of simplicity, I'm showing 20. So we have 20 features or latent concepts that are language independent. Okay, and so those features we can then use in a number of applications, like computing pairwise similarities across documents, or looking at cross-language retrieval, or some machine learning applications. And so so this little figure here in the lower right is actually taking this vector and just represent it now as a signature. And so we're saying that each document has kind of this 300-dimensional signature consisting of all the features. So we're using the Bible as our training set, and then we use the Quran as our test set. So we train on the Bible using SVD, and then we project some of the chapters of the Quran into that language-independent concept space, and then use, and since we know, just like with the Bible, we know which chapters of the Surah are related, or translations of each other, we then have a ground truth. We have 114 of those, and so we can then do some computational tests and actually look at the accuracy or the precision of how well we're doing. And I'll skip that last bullet just to save a little time here. So the performance metrics that we're looking at, these are all standard measures from information retrieval, but we've modified them slightly to fit for this language, for multiple languages. So the first one is what I'll call P1, or the average precision at one document. And so this is if we have, on the far left, if we have a query document and we want to find in a specified target language which document most closely matches that one query document. And if that document that's returned is actually the translation, for example, if we had the query document be chapter 1 in English and the one that it found is chapter 1 in Spanish, then we know that that we basically got that one right. If it was chapter 2 that we returned, then we got that wrong, so you got 0%. If we can average over all queries and just for that one target language, that gives us then the average precision. The other thing that we're actually more interested in is what we call MP5, or this average multilingual precision at 5. So since we're dealing with 5 languages, we'll say 5 here, but in the general case, it could be n languages. And so in this case, we're looking at, we have a particular query document, but we don't specify a target language, and we allow that query, we try to find matching documents for that query, and they could be in any language, any of our 5 languages, including the language of the query document. And if those 5 matches, we're looking at the percentage of those 5 being the counterpart of the query. And so that gives us then a percentage, and we want to go ahead and look at all queries and average over that. So this is actually more of a measure of success in doing multilingual clustering. And it's a much more difficult retrieval problem than this one up here. And so we're actually striving for about 90% MP5, which roughly says that 9 out of 10 of our documents will cluster together, regardless of language.
So you're trying to find all the documents, or just any language of any document of any language?
So if we start from any language, we have a query document. We want to say let's say we start with chapter 1 of English. We want to find all the chapter 1s in all the other languages. So.
Do you always have the other languages in the test set? Do you have queries which would have no correct answer?
No, there's always, it's always going to have a correct answer. So because we're dealing with the Bible or the Quran, we know which one should be matched up.
Yeah, you can remove them just to see whether.
Yeah, we haven't done that. Yeah, that's good point. Okay, so just some early results here. This chart shows precision at one document, which is the case where we specify the target language. So we have an English query, and then we look in Arabic, and also look in French. And so these bars, the gray bar on the far left in each case is basically just training on those 2 languages themselves. So training on English and Arabic translations, that's what we start from, in English and French. The rightmost bar in each of these cases, where we have in our training set, we have 47 languages, but we still only test on the 2 that are specified here. And so the general trend is that as you include more languages in your training set, you're getting better precision, okay, which is somewhat counterintuitive. You would think that, or maybe you would think, if you had more data in your training set that's irrelevant to your actual query, that your precision would go down. But we're actually finding that we're learning something else from the other languages, and that's kind of helping the query or the precision here. So
your concepts are getting better, probably, right?
Say again?
Your concepts are getting better?
Yeah, so they're kind of getting more refined because they're borrowing and leveraging information from other languages and making those relationships more explicit, and so that's how it's helping.
Yeah, in test time, when you query with the English document, and the first document returned is not Arabic, do you count it as a hit or a miss?
As a miss. for this case.
So even if you have 47 languages, just querying English and the first one returned as Arabic.
But it has to be. Well, we're specifying that it is Arabic, but it has to be. If we have a chapter 1 query, we want to find chapter 1 in Arabic.
So you return maybe 47, but then one of them is Arabic. That's the one you.
No, we're not even. Just ignore the 47 in this case. So while we train on all those, that's building up our latent semantic space, that U matrix, and then forget all the other 45 languages. Now we only focus on English and French or English. And
so you look at the first Arabic document that you retrieve with that pair.
So shouldn't. Oh.
And what was the distance measure you used?
So we're looking at a cosine similarity. So
Cosine,
cosine similarity.
No normalization, so no idea.
Say again?
Was there normalization like IDF or something?
Oh, yes. So that kind of goes back to the very beginning. So we started with a log entropy scaling of our original term document matrix.
Okay.
Sorry, I forgot to mention.
Shouldn't you're always using 300, independent of the number of 300 concepts, independent of the number of languages included in training.
That's right.
But wouldn't you be able to get away with more concepts with more languages because you'd be able to resolve?
Perhaps, yeah. We went with 300, partly out of the fact that when we started out, we were limited a little bit with the computational power we had, just running on laptops and whatnot, and also there's evidence in the literature that suggests that 300, that's kind of been a historical number, I think since the mid-90s or so. I can't remember which paper it was, but they used 300 concepts, and so we went with that. We did try, varying it from like 100 all the way up to 300, and 300 still performed better than the ones with fewer dimensions.
So I can see how 300 would. So the number. So this is the. So sigma is a square matrix of 300 by 300. Is that what?
Yes.
So I can see why it would be data driven, what that should be, but it should also be domain driven. Like for the Bible, 300 might make sense for certain purposes, but if you're applying it to the web, then
right. Yeah, so that's a good point. If you have a particularly rich set of documents or a very expansive set, then maybe you would need more. That's something we haven't explored.
Yeah, I completely agree. I'm Brett's colleague on this, and I completely agree. I mean, there's a handful of magic numbers here, and having a data-driven way of deciding how to set those numbers, or at least to know that you've finally tweaked all the accuracy you can out of these things, is an ongoing area of interest. And it just takes a lot of computational cycles to explore that parameter space, but we have those, which is more a matter of having enough human time.
Human time and funding. All right, so this is now just a more complete graph or plot of the results we had in this early paper. And so you see more language pairs like Russian and French and so forth. On the far right is just the overall, it's kind of aggregating all the results together, but the trend still holds. When you have few training languages, the precision is lower than when you have more training languages.
So just to make sure I understand this, so the way the sharing happens between different languages is because you give a unique document ID irrespective of the language. So if God happens in verse 3, 3 is going to be across the languages, right?
Yes. I understand your question.
I think you do. I mean, each column of that original matrix was devoted to a different verse of the Bible. And the first chunk of each column is the English language, the next chunk of the same column is the French language, and so forth. So all the terms in a single column relate to the same verse, and that's how the verse identity, that's the equivalent. Column ID is equivalent to verse ID in your question.
Right, then verse ID is common across different languages.
In that column,
yes.
Looking at this, it seems that the blue language pair is particularly good. And if we'll throw out the one afterwards, we'll probably do better. Now, did you try something more ambitious on these lines to choose?
No, not. We haven't tried anything more than this. This was something that was an interesting result, but then we moved on to more techniques. And so I'll point out that this is precision of one document. And so on my next slide, this is where we're getting into the thing that we're really interested in, which is multilingual precision, or MP5. And so in this table, this is the score that we're actually looking at. And so we started out at 26%, and then this is when we needed to actually leverage some more sophisticated techniques to get that multilingual precision up. And so we tried a number of things to actually get there. And so this is where I contributed some techniques and different ideas along with some others. And so just one technique, going from 26 to 65, if we take our log entropy scaling, that's what we scaled our matrix with, we can do some things to the global term weight to influence that. So the distribution of terms. And so this chart, I'm not going to go into any detail on that, but that's kind of one simple technique that we did to get up to 65.5. Another idea is now, instead of having all these language matrices stacked on top of one another, we can separate them out into a set of matrices where they all have the same number of columns, but because each language has a different number of terms, we now have a different number of rows for each matrix. And so there are techniques out there for looking at these collection of matrices and analyzing them all together. And so this is an actual expertise that I have, and I've kind of brought to this, where we looked at this Parafact2 model to basically do a decomposition of these set of matrices to get this individual U matrices. That got us up to 78.5%. But then we tried some more techniques, and one that we found that worked pretty well is this one called LSATA, or the TA stands for term alignment. And so I'll go into that in a little bit more detail here, but the idea is that we've included some term-to-term alignment information in our LSA technique. And this kind of stems from, there's a lot of different ways of computing the SVD. And so the SVD, x equals U sigma V transpose, can be computed by just taking our matrix X, multiplying by X transpose, and then computing the eigenvectors of that matrix, that square matrix. That gives us the matrix U here, with the eigenvalues would be the singular values squared. Okay. We can do the same thing for X transpose X, but there's another way of doing this whole thing where you actually get U and V together, and that is if you take a 2x2 block matrix, and so we have X and X transpose in our original matrix, and it's kind of represented down here. So we have a term by document matrix in the upper right, and then you take the transpose of that, and it's down the lower left. If you compute the eigenvectors of that 2x2 block matrix, you then get U and V stacked on top of each other, appropriately scaled by 1 over root 2. But you can then take that information out and retrieve U and V. So this is what we did. But we actually we were inspired by a paper by Bruce Hendrickson in 2007 that looked at how can we take, or we can augment some information in that upper block, this term-to-term information block. Similarly, you can also augment down here in this document-to-document block, but we didn't do that. So what you do is in this D1 block, the upper left, is we can maybe put some binary entries. One if the term in each language matches up with a term in another language. So casa in Spanish matches with house in English, matches with maison in French. So we can go ahead and put a 1 in those cases, in those entries where house, casa, and maison match up. Okay, and so we can then go ahead and compute the eigenvector decomposition of that, or get those eigenvectors, and then use those. Once we separate out the individual U matrices, we can then use those as our latent concepts.
So this is a little, as far as the number of documents and number of terms, that feature is not correct. You typically have a lot more documents, right, than terms.
That's right. Yeah, you have a lot more.
There's going to be a small part of that.
Yes. Okay. I think what I'll do is I'll skip this in the interest of time, but there is kind of a representation, or maybe I can cover this briefly. So the idea is that if we have, just in the normal technique, if we have house, casa, and maison, maybe the original method, just using LSA, would give us a large value for house in a particular column, but a small value for casa and a small value for maison. And so those are represented by the size of these blocks here, or these entries. So once we multiply by this D1 matrix that has that information more explicit between those terms, that then makes those values the same in magnitude. Okay, and so that's kind of the rationale behind this particular method. And with our particular scaling that we used, it's listed here. We're actually getting up to multilingual precision of 5 documents, about 80%. So we're on our way to 90%, but still not there. this is where then we turned to a different technique where we looked at language morphology. And so there's a question very early on about, so why are there different number of terms for English and Arabic? And so the answer is that languages are in the spectrum of between isolating and synthetic language. So an example of an isolating language is Chinese. English is also largely isolating. And so here's an example from Wikipedia. So he traveled by hovercraft on the sea is the example that they give. There's generally just one morpheme per word, a morpheme being kind of the smallest individual unit of meaning in the language. So he is a morpheme. Traveled actually contains two. It has travel, the base verb, followed by the suffix ed for the past tense marker. Okay, so and then hovercraft is a compound noun. It has two morphemes, and then all the rest of the words are just a single morpheme. So that's one example on one end of the spectrum. Synthetic languages, on the other hand, have a lot of morphemes per word. And so there are some examples, like in German, where you have these very long compound nouns. My favorite is this one in the very bottom, Eskimo, where this one single word means he had not yet said again that he was going to hunt reindeer. And so somewhere, so if that had changed to be she had not yet said again, and so on, somewhere in this word that's going to change. And so in our latent semantic analysis example, or that framework, we now have an individual term or a different row in our matrix that would correspond to the word for she had not yet said again. Okay, and so that would kind of break the co-occurrence, or allowing us to find the co-occurrence information.
How do you do the segmentation for everything?
Say again?
How do you do the
I'll get to that.
segmentation?
Is that how they write it?
I don't know. I'm not an expert, but I grabbed this from a textbook that my wife has, and so.
It would be a pretty big coincidence if they were using the Latin characters, right?
Yeah, I don't know. Maybe this is more of a phonetic spelling. I'm not quite sure.
Yeah, they may not have had their own script. They may not have had their own indigenous script.
So then somebody came and said, "Oh, this is how you should write it." But maybe there was segmentation if they were to write it.
Perhaps. Yeah. Like I said, I'm not an expert in
spaces.
So that then led us down this path of looking at morphological tokenization. So our hypothesis is if the terms in our LSA analysis were morphemes instead of words or stems, then our results of information retrieval would be improved. And so two approaches that we looked at were tokenization based on mutual information of character engrams, and the other one is looking at minimum description length as a technique used by Goldsmith in an open source tool called Linguistica. And we've actually used this, the Linguistica approach more, or at least we found it to be easier to use. But I'll go through and just kind of describe the first one just a little bit, since I know at least Moshe is interested in language morphology, so I'll talk about that.
Related to the second one, I guess we read a paper by Snyder and Barzilay, which follows up on the Goldsmith work. I think it might be interesting.
Yeah, talk to me afterwards, and so I can write that down. I'd be interested in that. All right, so the nice thing is that these approaches are generalizable to new languages. So if we come across a language we haven't seen before, there's no language expert, we can use these unsupervised approaches to kind of do this morphological tokenization. So that one approach, tokenization from n-gram mutual information, we take the words and we consider all possible tokenizations of the word. So take, for example, the word walked. So walked, we can just go ahead and consider that as a full term. We can maybe split it between the W and the A, or between the A and the L, all the way down. Or maybe we consider multiple splits in that word, and so we can split in many locations. What we do then is we calculate the pointwise mutual information, or PMI, for each n-gram individually from the corpus. So one example is the pointwise mutual information of walk is just the probability of walk in our corpus divided by the probability of all individual letters appearing by themselves. Or not appearing, but actually those letters appearing in the corpus. And then we can take and sum those pointwise mutual information scores for each tokenization, and then select the result that is closest to 0. And so we'd have a whole list of those, and we can look at the one that has the score that's closest to 0. Maybe it's the one here in the middle, but most likely it's not the one at the very end here. This one where the split is kind of awkward between the A and the L.
So just to clarify here, do you take the text and do all possible tokenizations uniformly with equal sort of probability, and then you start counting to get your mutual information?
Let's see. So we look at our corpus. I'm having trouble understanding your question, I guess.
Well, you showed there's various ways of splitting walked,
right? Yeah.
If I see walked in my training data and I want to go and calculate probabilities for those particles, if you want, adjacency, because you want my answer, which split do I walk? Sorry, which split do I consider? Do I consider all of them?
You're considering all of them, and so you're looking at the probabilities of walk and ED, for instance. How often do those appear in your corpus? And so then because not only you have walk or walked past tense, but you have talked, all the other ones that end in ED. And so because of that, you'd have a large. It'd be more likely that you'd pick walked, split this one here, walk in the past tense marker ED, than any other one.
Maybe it will become more clear if you define the probability. So in the case for walk, for example, what's the denominator? In the case of ED, what's the denominator? Are they the same or are they different?
So so in this case, walk has just the denominator.
In the probability itself.
PR.
Oh, I see. It's the total count of the. Good question. I think it's all of the instances of the word. I'll have to go back, or maybe we could look in this paper. I can't remember exactly what it is in the denominator. I can't think online here.
Another question here. How do you deal with exponential complexity?
We're not worried about that at this stage. So
okay.
It's just a research activity.
But the denominator there in the PMI for walk can be many things, right? I mean, it could be walk.
Are you talking about the denominator, this thing here?
Yeah. I mean, why would you choose that particular split? You just showed you can split walk about 2 to the n ways.
But it seems to me that those unigrams, they just drop out, actually.
Yeah. So actually the denominator doesn't, So because we're dealing with the same word, so imagine, so the PMI of walked is going to have WALKED in the denominator here. Because it's a logarithm, you could split it out and you have log, the log of the numerator minus the log of the denominator.
That's not my question.
And so,
let him finish, right?
Yeah. And so once you have that, you can go ahead and all the denominators here in the bottom, you can just go ahead and ignore. And so you're only considering the numerators for this PMI expression. Make sense?
It makes sense, but...
All right, maybe let's talk afterwards. So these are some sample tokenizations, and I believe this is with MDL. So these are the first 3 words are from French. The second set of 3 are from English. And so you can see cases where it's splitting where you might expect to see good splits.
So are you setting a hard limit on the number of splits?
So with MDL only splits in one place, and then if you want to split a second time.
Okay, so that solves the computational question.
Yeah, but that's only for MDL. The other approach that we were talking about, it doesn't matter that you can split multiple ways. You can go ahead and set it so if you just wanted to look at one split, one tokenization where you have 2 morphemes, you could do it that way to limit the complexity.
Say it again. Sorry.
So I think the question is, are you worried about the complexity of trying to find all these tokenizations? And so, if we were to allow all of the tokenizations, all splits, that's going to be very complex. But we could go ahead and limit it to just have one, a single split in a word. Okay, and then if we wanted to redo it, just redo the analysis to then find a second split.
So you do it greedily, basically. You find a one split, and then you say, okay, let's commit to that split, and let's say if we can if there are splits that bring some value.
That's
also
right.
at the point, okay.
Yeah. And that's basically what MDL does. Is they're just looking at a single split first.
Okay.
All right, so now we can go ahead and replace those terms with morphemes in our term by document matrix. So now we have a morpheme by document matrix. And we call this technique Latent Morphosemantic Analysis, or LMSA. And because we will actually have fewer morphemes, so this will be a smaller matrix, fewer number of rows, but the matrix will actually be a bit more dense. And so that's this is the premise for this technique. The results for that, if we compare by language, so LSA is on the bar on the left, and then this new technique dealing with language morphology is on the right for each of these cases. You see that across the board, adding in language morphology does help.
When you did LSA, you didn't do any stemming at all?
That's right. Yeah.
Did you ever with just doing some simple stemming? Say taking the first
I didn't, but I think my colleague did when he first started, but I'm not so sure on that. It may have been because we didn't have the stemmer for other languages.
Just like taking the first 4 characters of each word or something basic.
Yeah, we have looked at like doing character n-grams and doing an analysis there. I can't remember the results. We've published on that work elsewhere, but I can get that to you. But I can't remember offhand what it is. All right, so this is now kind of revisiting that table that I showed you before. So LSA TA got us up to 80.7. The language morphology actually dropped us down a bit to 73.7% for the MP5 score. Now let me describe the final technique, which is combining the language morphology with the term alignment to get us up to 88%, which is pretty close to our goal. And that is just, we want to use the language morphology, so we have morphemes by documents. So we have a morpheme to morpheme alignment matrix there. And then we have some scaling in there, and that gives us multilingual precision at 88%. Okay. So let me go ahead and.
Right.
Yes.
Someone does. I don't even know the answer to this question. Where did the term alignments come from? Was there a standard lexicon of translation?
Yeah. So that was actually looking at mutual information once again. So we can look at the mutual information of various words appearing in the parallel corpus to determine what those are. I think I had on the slide. I mentioned that we could actually have ones and zeros in that matrix. We could have ones and zeros here. Just looking at a cross-language dictionary, or we can go back and look at the mutual information of where those terms co-occur and so forth to actually get a numerical value that's not a 1 and a 0. And so that's the approach that we used. All right. So this slide kind of summarizes the results for some of these techniques. The one that we've been going with, or at least gives us the best precision, not necessarily the one we always use, but because it does require some extra work, is this latent morphosemantic analysis with term alignment. And so you see the bar on the right, which is the multilingual precision, is generally pretty high. So we're at 87%, 88% there. The bar on the left in each of these cases is the precision at one document, the one where you're specifying the language pair, and that's the easier of the two. So you see that basically compare these methods across the board. So now we can just do a simple example. We can cluster some documents, in this case just showing clustering the books of the Bible. Not really a good example since we're training on the Bible, and now we're trying to cluster them. Really what we wanted to do was train on some corpus and then try to cluster documents from another corpus. But this kind of gives you a sense, since a lot of people know some about the Bible. So these nodes in this graph are colored by language. And the books cluster first by their counterparts in other languages and then cluster largely by topic. So the New Testament is clustered up in the top part of the graph. Old Testament is more on the right. The Gospels are down there. So let me zoom in on the Gospels. So you see that the book of John and the book of Acts actually have tight clusters. The red links indicate that they have, there's a strong similarity between those documents. But we do see some mixing in Matthew, Mark, and Luke, and so Bible scholars call those the synoptic Gospels, and so there's it would make sense that they may cluster, kind of have some mixing because they do share a similar perspective.
So how's this picture made? Is it?
So I kind of glossed over that. So we're doing some we have some visualization software that does the graph layout and a particular layout algorithm for doing the clustering. It's a what do we call it? You have springs. Force-directed layout is what we've got.
And so you give it the distances, and the distances here are
pairwise,
cosine?
Yes, we have a pairwise similarity based on the cosine similarity between documents, and then it goes into the algorithm, and it's treating those values as spring constants. And so with a higher value, that's trying to keep those documents closer together. And as the shape starts to take place, as things start to line out, the algorithm actually starts to clip some of those springs if they get too far stretched out, and so then it allows to kind of spread out a little bit more. And so that's this algorithm here at VXORD, and it was developed at Sandia back in 2005.
Do you do anything special to the cosine distances before you put it in there, or just?
Do I know anything special about them?
Do you do anything? So these are. I'm trying to understand the lengths of the edges are. Are the lengths of the edges the cosine distances? Or?
No, we're not doing anything like that. You could do that where if you were to look at, like for instance, multidimensional scaling, where you want to do a lower dimensional embedding that tries to preserve the distance between documents based on the distance in the higher dimensional space. You could use MDS for that. But that's not what we're doing here. This is a different algorithm. It scales. It's much faster than doing MDS, like that sort of a layout.
Yeah, one of the implications though is that you shouldn't look at the length of the lines as more than just an evocative measure of how close the documents
Okay,
are.
that was my main question.
But on the next slide, as Brett showed, some of the lines are the color is a safer bet as to the tightness of the connection rather than the length of the line.
All right, so let's see. You told me to finish up about 5 till. We're getting close. So I've got a few things to show still. I can show some high-performance computing or these text classification problems. What's more of interest to folks?
Text classification.
Text classification? Okay. All right. I'll just show the highlight, though. For the high-performance computing result, we try to cluster 1.25 million documents of the European Parliament proceedings and try to do that as fast as we could. All the data resided on a network, on a high-performance computer. And in this case, it was Jaguar PF. PF stands for petaflop. And so on 32,000 cores, it took just about 8 minutes to do. And so the whole idea here was trying to do this in what we call analyst time, so that when an analyst has some idea in their head, they want to get the answer as fast. We don't want to wait for a day to submit a batch job and have the result come back later. So let me skip now to the text classification problems. So we looked at 2. The first one is, can we predict ideology in documents? In this case, we specifically looked at, can we find hostile ideologies? And so we're kind of defining hostile ideologies as those that are hostile to democracy and so forth. So our hypothesis is that there may be a link between religious texts and threats. And since we've used the Bible as a lens to look at these documents. There may be some regions in this document feature vector that would indicate some amount of ideological content. So we constructed a data set that had 250 documents of different languages, but they all consisted of some documents from Lenin, Hitler, some from the Middle East, and so forth. And then we supplemented that data set with 9 times as many web documents randomly sampled from the web. The approach then is that we create some feature vectors of all 2,500 of these. So now we have some feature vectors to train a classifier, and then we used this predictive model to predict ideological versus non-ideological. So we're trying to predict B's from the randomly selected set, and also looking at just the first 2. Can we distinguish between the first 2 here? And so the next slide we have the results here. So we have the hostile ideology versus the non-hostile. The baseline accuracy is 90%. We actually were able to get up to about 99%. And this is using an ensemble decision tree classifier. And then we also have, in the second category, looking at Marxism, Leninism versus the documents written by Hitler. We're getting up to about 95%. But when we compare those classification problems versus one that's out there for doing sentiment analysis, looking at movie reviews, where we have positive and negative movie reviews, we're actually not doing as well as what's published in the literature. They're getting up to something like 75%, and whereas we're getting about 65%. And I think it's because we're looking at these documents through the lens of the Bible, and that's kind of relates to the question that was earlier about is this really the right thing to be looking at web documents? Lastly, we've explored some ideas of looking at multilingual sentiment analysis, and so the idea here is if we're starting solely from an English sentiment lexicon, so these are like words like happy and pleasant and fun, these all kind of denote a happy feeling, pleasant feeling in people versus ones that are not as happy like funeral and death and so forth. So can we look at that if we use just an English sentiment lexicon? Can we look at the other documents and classify their sentiment? So our approach is we label some chapters of the Bible. We picked a subset of those. So I'm indicating those just in this figure here, kind of red and blue, the positive and negative. We can then project those particular chapters into our language independent feature space, train a predictive model using Avatar, which is the software that at Sandia for doing ensemble decision trees. We can then once we have that predictive model, we can then look at the other documents in the other languages and then compare back with the actual labels in our from the ones in English. And so when we train on French, Spanish, and German languages, we're getting about 72% accuracy. So certainly better than random, and but not as good as we'd like. All right, so I think. So I think that kind of concludes my talk. So what we've done here is we've created a framework for doing a number of things. And so by taking these documents in multiple languages, we can project them into a language-independent feature space, do a lot of things with computing similarities and doing clustering, some text classification problems. And we actually have a lot of other text analysis work going on at Sandia, believe it or not. And these are just some of the things that I've been involved with, and I can talk more intimately about these topics if there's any interest, but I think due to time I'll go ahead and finish here. The last slide is just a list of all the references. So, all right. Any other questions? Yes?
Do you know how crucial it is to have perfectly aligned documents?
Yeah, that's kind of the heart of the matter here for us. Because we're starting with the Bible, it's very fine-grained parallelism, a sentence or two in length, and we know that those sentences in other languages should match up with what we have in English. If the parallelism gets much, if the chunks are much larger than that, then I don't think it would work as well. We actually haven't tried it, but that's an educated guess.
So how would you get away from the Bible?
So we've looked at I think it's simple. You just go ahead and add. You can add more things than just the Bible. We can add more corpora, so we'd have in fact we've done this not where we've augmented the Bible, but we've replaced the Bible with the European Parliament proceedings, and so now the lens that we're looking at other documents is more of a political context or some world issues. You could look at things if you included textbooks, for instance, then you get more technology in your concept space. So the idea here is if you take all of that together, Bible, textbooks, your Parliament proceedings, these sorts of things, then you have a large corpus to draw from, to get at your underlying latent concepts.
So if you want to do that, are you going to be able to handle missing languages in one of your corpus? Let's say you take the Bible plus the European Parliament proceeding. So you have an Arabic translation of the Bible. I imagine that the European Parliament proceedings are not translated in Arabic. How are you going to deal with it?
That's certainly a research question that I'm interested in, and I think developing some computational techniques that can deal with those missing blocks. You've got missing data. How do you deal with that effectively? And that's a research question I'm interested in. Yeah.
So in your experimental setup for the multilingual precision, have you tried using just the dictionary data or just the PMI for the used for the term alignment part?
Yeah, so I think I don't think we used any dictionary information, partly because it was easier just to deal with the corpus that we had and just run our studies, but I think it would be interesting to actually include more explicit and refined relationships as provided by an outside source
Right, but one could also just try to use the mutual information like metrics you have right now without using any of the SVD-based concept space, right? You could just take the term vectors from one side, chop them up into smaller pieces, and send them through your term-by-term similarity, and see what comes out in the end, and whether it still manages to find.
Yeah.
Without using any of the SVD stuff. But.
So we've done something similar to that, if I understand it correctly, just looking at doing the computing eigenvectors of that D1 block, that term-to-term block, and so that actually does fairly well.
Right. Yeah.
I don't know the numbers on that, but it's very competitive. Any other questions?
Did you try using word alignment tools?
Word alignment tools, I don't think we used. I'm not aware of using any word alignment tools.
It's basically those numbers that you stick in your term-by-term matrix. I think we have tools to give you better kind of parameters for that than just mutual information or whatever you're using. That basically resolve through some competitive analysis what words in each sentence align to what words, like which things co-occur.
Right. Oh, that'd be fantastic. Yeah,
because they actually belong together.
Yeah.
So it might just help you out.
Yeah, I think that'd be great. So let me know after this. So I can write
sure, I'll give you a little more information.
Is no one in Sanya doing machine translation down
there? Not to my knowledge. Philip, do you know of anybody?
No, we don't actually do machine translation at all. It's not, analytically. I mean, to the extent to which we need actual translation tools, we either buy them in popular languages, people like LMSATA, or some people who consult with Cynthia have their own translation resources, but it's not been a research line for us. In fact, even this work came. Cynthia has a need to do this sort of thing, partly because part of what we do is just technology surprise investigation. We look at what our country is capable of and other countries are capable of and project what they're going to be able to do in the future. And to do that, you have to track their scientific literature and so forth, and multiple language skills are useful there. But we started off with this work because we had skills essentially in linear algebra and multilingual and tensor analysis and so forth, and found a fertile field of application rather than having a direct need to do language in the first place, which I think is how we got into it.
So something really interesting was that when you showed the performance of different language pairs, some of them were really bad and some of them were really good. I mean, in the kind of your earlier experiments, so Spanish Arabic was like at 50%, even though English French was at 95%.
That's right.
And we're used to seeing that difference, but I've always chalked it up to kind of we have more data in English French, which isn't the case here.
Yeah.
Or we have it's harder to generate French, or it's harder to generate Arabic because it's morphologically rich. But here, I think there's a little bit more of an even playing field. So it's interesting that you saw that big difference.
So in that we've always ascribed it to just the language family. So Arabic is a more complex language than English, and so trying to get those co-occurrence relationships, those latent relationships out of that analysis has been more difficult. And I think that's what it's due to.
And do you still see those big differences after you add the kind of term-by-term?
Yeah, it's always there.
Matrix?
So it improves it, certainly. But Arabic, Russian are the ones that are typically lagging the others because, English and French are very closely related and Spanish isn't too far off. And so those are able, when we look at the statistical co-occurrences in those languages, it's easier to find them as opposed to in Arabic and Russian, because they're just different language families.
What's kind of troubling about that is that there was a question earlier about, why does it even help to have multiple languages in the queue? And there was a comment that was made about maybe that's helping to explore, giving you a bit more refined sense of the concepts involved. And one hypothesis we've had is that multiple languages helps with polysemy. The idea is that polysemy isn't conserved across language families. So although it can be confusing, it's just French and English or something, it's not going to, the same polysemic pairs aren't going to be existing in other languages. And so maybe that's why adding languages helps. But if that's the case, it's confusing why adding Russian or Arabic causes things to tank, because there's such a distinct language family that seems like if that was a useful contribution, it'd be even more useful there. So there must be either that's not the correct hypothesis or there's a compensating disadvantage or something we haven't teased out yet.
But isn't there a simpler explanation that basically just says, if you only run your SVD on 2 languages, then a lot of the work that the SVD is doing is finding synonyms within each language. because it's kind of finding.
Sure, exactly.
And whereas if you put kind of more languages there, then kind of what you're going to learn tends to be more multilingual or something.
Yeah, I think so. I mean, I think exploring polysemy is a way of looking at that. I mean, it's the fact that polysemy doesn't conserve over languages that causes, I think, SVD to sort of spread its modeling strength. You know, and one thing we've been looking at, I mean, I'd be interested in anybody in this room has thought about this, is that, you know, essentially what Brett talked about was sort of LSA methods for looking at this analysis. But LDA is a popular technique for looking at some of this stuff. And there's been claims, at least, that LDA is, you know, more suited for dealing with polysemy because of the way it distributes its weights. And we've been thinking about, but haven't yet constructed an experiment to actually do a head-to-head of LSA or LDA for precisely this purpose. But I'm interested in doing that because I think it might tease out some of the LSA versus LDA influence on this kind of concept modeling.
There's yet another family that is the non-native matrix factorization.
Right. Yeah. So non-native matrix factorization is a technique, but it doesn't work as well for projecting new documents into the space. It's good for just doing an unsupervised clustering of what you have.
Right, but I think the main complaint here is that you put in positive quantities in particular counts many times, although you don't have counts, and that's not what, for example, these matrix factorization techniques are meant for. They were, you know, Gaussian assumptions.
Yeah.
They're just not true.
That's right. Yeah, and that's why they do the scaling. You have like log entropy scaling or term frequency, inverse document frequency scaling. These sorts of things try to account for that. All right. Well, thanks for your time.